Okay, we're going to do another problem in the area of conservation of energy. So we'll start off with our typical roller coaster on top of a hill, but let's change the problem up a little bit. What we'll do is we'll let it go down to the bottom, and then we're going to come up onto a plateau, and we'll make that plateau 50 meters. And then what we're going to do is, while it's on that plateau, actually, let's let it drop back down to its original height. And then, at the end of that, we're going to put a spring that's going to bring it to a stop. And that spring has a spring constant K. Now, just so you know, my students always make fun of me and say that, what's that symbol? That is my cursive K. It's mine, don't talk about me. All right. Now, so this problem we're going to say has an A, a B, and a C. And this is what you have to get used to when you do this type of problem. Every time you get to a different part of the problem, you start over. So if I do my conditions where I simplify in the A section of the problem, then I'm going to go back and say the general equation, and I'm going to look at the new conditions. The new conditions will be my new initial, and I'm solving for a new final. If there's a C part of the problem, then I will consider that new condition my initial, and then I solve for my new final. So get accustomed to starting over. You're still going through the same process. So our A part of the problem is, what is the velocity of the car when it's at the bottom of the hill? Our second, or our B part of our problem, will be, what is the velocity when it's on the plateau? And then our C part of the problem will be, how far is the spring compressed after the cart comes in contact with it and the spring brings it to a stop. Let's get started. So our initial condition is it has MGH, it's not moving, and it's not in contact with the spring. So this would simplify to MGH. There is no kinetic energy due to a spring, and there is no, potential energy due to a spring, and there's no kinetic energy because it's not moving. Okay, so this is 0 and 0. In the final conditions, it's moving, but it's at the bottom, so it has no potential energy due to gravity, and it's not in contact with a spring, so it has no energy due to a spring. So this would go to 0, this would go to 0, and it simply has 1/2 mv prime squared. So our problem simplifies to MGH equals 1/2 mv prime squared. We can cancel our masses and solve for the velocity, so this becomes 2gh, or the square root of that, equals the velocity of the kite when it's down here. So you could plug in your numbers and get your right answer. Now you know the velocity when it's down here. Let's do our second part of the problem. So that was A. Part B, we start over. Now, here's the beautiful thing about this, this process. You could use your initial conditions as what you had up here, or you could use your initial conditions for here. It won't matter, because you know what? They're the exact same number. Because when the object was up here, all of the energy was potential. So let's just pretend that that was 10,000 joules. Well, all of that energy got created into kinetic energy when it's down here. So it's still 10,000 joules, but the joules are in form of kinetic energy and opposed to potential energy. Now, so take your pick. I'm just going to pick down here as our new position. So going through the system, down here, does it have potential energy? No. Does it have kinetic energy? Yes, because it's moving. What velocity is it moving? It's the velocity from the previous part of the problem. So though we called it prime here, we're going to call it just plain V in the B part of the problem because those are our initial conditions for this part of the problem. So it doesn't have potential energy, it has kinetic energy, and it's not in contact with the spring, so we just have to write not MGH, but 1/2 mv squared, where that V here is equal to our V prime that we solved for there. Now, let's go to our final conditions. When it's up here, does it have potential energy due to height? Yes, because it's 50 meters above the ground. So it has mgh prime, where the h prime is equal to 50 meters. Is it moving? Yes. Now it did slow down because as it went back up the incline, it converted some of the kinetic energy back into potential energy. So it lost kinetic energy and slowed down, but it gained potential energy because it was going up. So it does have kinetic energy, it's just not as much. So this is our new V prime. So we want to know what is the velocity when the kite is now up here. So now we take this equation. The masses, guess what? They're the same, so you can just go ahead and cancel them. And then, so let me rewrite this. And you don't have to cancel the masses if you don't want to. Whatever you feel comfortable with at this time. So now we just need to solve for the velocity. This is getting a little cluttered, so I'm going to move over here so you can see it. I'm just going to bring the GH on this side. So this is going to be 1/2 V squared minus GH prime, where h prime is this height right here. In fact, I'll say h prime for this part of the problem is 50 meters. And that's equal to, we left that over here, 1/2 V prime squared. So just bring the 2 over by multiplying both sides by 2. And these 2's will cancel. Therefore, your final answer becomes 2 times 1/2 V squared minus GH prime equals V prime squared. So we can just go ahead and take the square root of this side. That gets rid of the square. And now you have the velocity of the kite when it's on top of the hill. Don't let the algebra scare you. Just rewind this and see how I canceled it again. Again, really quickly, what I did is I brought over the GH to this side. So I brought it from over here to here. That's how it got the negative symbol. Then you just had 1/2 V prime on this side. I canceled the V out by multiplying both sides by 2 so that you end up with this. To get rid of the square, you take the square root. You now have your final velocity. So now you have the velocity of the kite after it goes from the bottom to the plateau. It's a little slower, but it's still moving. We'll do the spring in the next part of the series so I can clean up the board a little bit.